Today I'm going to start writing code for two-dimensional transformations. First we're going to start by writing it with code that's included with MonoGame. Then we're going to try and improve upon that a little bit by making our own routines. Since the vast majority of the transformations that we're going to be doing are two-dimensional, since this is a two-dimensional game library, we can probably shave off some memory considerations because we don't need a general three-dimensional transformation matrix. The matrix structure that comes with MonoGame is built for general purpose three-dimensional transformations. Let's get started by first doing it the way that comes with MonoGame. I'm in the game class right now. I'm going to go ahead and remove a lot of this code that we're using to test our circle drawing. So we don't need that anymore. Here's where we created all the circles. I'm going to remove all of that code. I'm going to keep the stopwatch, but let's go ahead and get rid of the circle array we created. And we don't need the circle struct anymore, so I'm going to get rid of that as well. Let's now go into our shape batching class, and we created this draw polygon routine that simply loops through all the vertices and connects them with lines to make a polygon. I'm going to add one more field to this because I want to be able to now transform these vertices by a certain amount. And what we're going to add is a matrix and I'm going to call this transform. Matrix is a structure that comes with MonoGame, which is basically a 4x4 matrix of floating point values. We can scale, rotate, and translate any point we want using this transform. So how we're going to do that now is we take this matrix and we're going to apply it to the vectors that we have. So we're going to now say A is equal to vector2 transform. Transform is a static function that comes with the vector2, which allows you to transform two-dimensional points. We're going to transform A by the matrix transform that we passed in. And then we're going to do the same thing for B. And just like that, we should be able to transform the points by any world transform that we want to specify. Now that that's done, we can go back into the game class. Let's go ahead and create a polygon. I'm just going to have a vector array. I'm going to call this vertices. Let's make it private. Inside initialize, let's actually create some kind of object that you might see in a game. We'll make a new vertex array of vector2s. I don't know the length yet. We'll just go back to this drawing program and let's go ahead and create some kind of object. I'm thinking spaceship or something similar to that, or lunar lander. This is our two-dimensional grid. I want to draw some points. So I'm going to have the first point up here. This will be the top of the object, and it's going to look like a triangle. We're going to go down over here, and then I want some points here and here. When I connect these, it's going to look something like this. I'm just going for something that looks like that you might see in an old retro vector game. And so I'm going to call this vertex 0, 1, 2, 3, and 4. So we're going to need 5 vertices. Let's go ahead and specify that here. So we want 5 vertices. Then we're just going to explicitly write out each point, or specify each point. The first one is going to be, the x is at 0, we're going to stay there, but the y kind of depends on what we're making, but let's just go up 10. It's going to go 10 that direction. On the x we're 0, on the y we're going to go up 10. I'm going to copy this and just make 5 of them. This will be 1, 2, 3, and 4. The next points, I think I want to go down just as far as I went up. Not exactly to scale, but I'm going to make this down 10 here, so this will be a negative 10. And then I also want to go 10 this way, so this will be a positive 10 in the x direction. So we're going to have a positive 10 on the x and a negative 10 on the y. 10 and a negative 10. That's point 1, point 2. Actually, I'm going to specify these last. Let's do this one next since it's just kind of the mirror image of the last one we just created. That's going to be now a negative 10, but on the y, negative 10 on the y as well. Now these middle points, I'm thinking going out maybe 3 on the x, and we'll just say 6 on the y. So this will be a negative 6 and a positive 3. Let's just see what that looks like. So we're going to go positive 3 and a negative 6. The y on the other side, let's give this. So now we're just going to go to the other side over here. So the y is going to stay the same on this one, but then we need a negative 3 on the x. Let's put a negative 3 here. So we have our vertices. We should be able to now draw this using our shape batching routines. So let's tell the shapes that we want to draw a polygon. We have the vertices. We don't have the transform yet. The thickness of the line is just going to be 1. And let's just make it white. Maybe a high contrast color against the black background we have. So now the transform is the next thing. In MonoGame, if you want to make a transformation matrix, let's just call this transform, you have different static functions inside the matrix class. The first one is going to be the scale. We're going to create scale. And you can provide a floating point, you can provide different overloads here, you can just provide the components. If you just give it a floating point scale, it's going to make all the components of that. So there are 3 components. There's an x, y, and z to the scale. If you just specify the 1, it's going to make all those components the same thing. Next, we want to specify what the rotation is. We actually have 3 different rotation functions. Create rotation x, y, and z. I might be able to draw, we'll see if I can draw what this looks like. If we're going to rotate on the x, that means we're going to now rotate around this x dimension, which if you're looking at it this way would mean it's going to rotate like this on the screen, this way. If you do the y, it's going to rotate around this, which is kind of hard for me to draw in 2 dimensions. But that now means you're going to rotate this way, okay? So kind of around, if you're looking at it flat like this, it's going to rotate like this. But what we actually want in most of our 2-dimensional programs is to rotate like this, okay? We want it to spin around this direction, and that's the z, and the z will actually rotate around here like this. Let's tell it we want a rotation z, and the amount of radians, let's give it a little rotation. Let's bring in the 2 pi radians, and we'll divide that by, actually maybe let's give it a little bigger rotation. Let's divide by 10. And then finally we want to create the translation. Where is it actually positioned? What's its world position? So we do the create translation, and then we specify where it is. These are all 3-dimensional points. Okay, MonoGame is using 3 dimensions, even though we're just going to disregard the z point, or the 3rd dimension, because we're just basically doing 2 dimensions. Let's just specify the components. We're going to leave it at 0, 0, and 0. So based on this, we're not going to see any scale because I'm keeping it at 1. We are going to see a small rotation on the z, and we're going to see no translation. Let's go ahead and place that transform in there, and let's see what happens. Okay, there we go. And we should be able to zoom in. I think we have that feature. And that looks pretty much like what we wanted using vector graphics. It's rotated to the left there by 2 pi over 10, whatever that is in radians. 1/10 of the whole way around, I guess, is what we did. Normally it would be facing straight up, since that's the way we created it. Let's go ahead and put something in for the y. Let's put a positive 100, and it should move it up 100 points. And so you can see it's actually up here now by 100 points and rotated. Now when you're using transformations, it's very important the order of your transformations. We want to create the scale and the rotation first, and then you want to apply the translation. Okay, and by multiplying in this order, that's what you end up getting. You end up getting scale, rotation, and then translation. If we did the translation first, then you're going to start seeing the object rotating differently. For example, if we translated first, we'd end up with the spacecraft over here, and then it would end up rotating like this. Like the whole thing would curve around the origin like this. But since we're at the origin when we rotate, it rotates it, and then it moves it. So we're going to see the rotation first, and then it's going to move it to the point where it's located, okay, or translate it to where it's located. So that's why we want to do it in that order. That is actually good enough. You could actually do everything in your game using that. But I'm thinking since we are a 2-dimensional game library, we can probably improve upon this. Well, first of all, everything's being done in 3 dimensions with a general purpose transformation matrix. We want to have very specific transformations done in 2 dimensions only. We should be able to make some smaller structures to store that information and do the transformations a little bit quicker. I downloaded the source code for MonoGame so we can look and see what they're using. And if we scroll down here, we can open up the matrix class. So this is the matrix class that comes with MonoGame. And if we look at the public fields, we have 16 different floating point values. Because to have a general purpose 3-dimensional transformation matrix, you need a 4x4 matrix. Since we're working in 2 dimensions, we should be able to make a lot smaller matrix to represent the data we need. So I'm going to make a structure inside of our flat library, and I'm going to call this flat transform. This is simply going to be a structure that's going to contain all the data we need to transform any point in 2 dimensions. We're going to have a position on the x, we're going to have a position on the y, a sine value for the rotation, a cosine value for the rotation, a scale value on the x, and we're going to have a scale value on the y. You can already see that in order to use the transformation matrix that comes with MonoGame, you need 16 floating point values. Well, we have 6 floating point values. And if you do the math, 6 times 4 bytes each, so we need 24 bytes for this structure, whereas the matrix structure for a 4x4 matrix needs 16 times 4, which is 64 bytes. So if we do 24 divided by 64, we're at 37% or 38%, basically a reduction of about 62%. We reduced the cost, or the memory cost, by 62% to store the transform data. Okay, and so let's just quickly create this transformation structure. Okay, so the first thing is going to be a vector 2, and that's going to contain the position information. So this is all going to be information that we want to use to transform. So this will be, where do we want to put the object? We want to transform it to this position. Next, we're going to tell it the angle, and this will be the angle of rotation, okay, the z. Then I want to tell it the scale, which will, let's make it a vector 2, since we're going to be able to have 2-dimensional components for the scale. And then we'll just pass through the data. So the position x is just going to be the x, and I'll just fill out the rest of this really quick. The sine is, now we're going to call the sine trig function on the angle. Cosine is going to be now the cosine of the angle. And basically all we're doing here is we're just pre-computing the sine and cosine so we can use it later. We could actually just save the angle and just say we have an angle and we're going to save that to angle. But then every time we wanted to use it, we'd have to compute the sine and cosine. So instead of storing the angle itself, we're just going to pre-compute the sine and cosine and then use that sine and cosine to perform the transformation. Let's save the scale, and that'll just be scale x, and then the y scale for scale y. That'll contain all the data we need to perform a 2-dimensional transform. And I'm going to create one overloaded constructor, and I'm going to pass in a scale that is just a floating point. And that'll mean that we want the x and y components of the scale to be the same. And so we'll just make this the scale. That should be most of what I need right here for now. Let's go back to our utility class. Inside our utility class, I'm going to add a new function, and this function is going to allow us to transform 2-dimensional vectors by using our flat transform structure. So this is a static function that's going to return a transformed vector. I'm going to call this transform. We're going to pass in the vector we want to transform. We can call this position. Then we're going to pass in the transformation structure. And so just like before, go back to the game class, you can see how we did this in very specific order, like we scale times rotation times translation. Think of it as we did the scale first, and then we did the rotation, and then we did the translation. We need to do the same thing inside of our utility for transforming. So the first thing we're going to do is perform the scale. So I'm going to make a local variable for the scale x. I'm just going to call it sx, and that's going to be the position x times the transform. And I named transform wrong, so let's put transform in there. There we go. Okay, that'll be times the transform and the scale x. And we'll do the same thing for the y component. Okay, so scale, easy enough. Just multiply by the scale, each component by the scale. Rotation is going to be a little bit more complicated. We talked about that actually in our previous video when we talked about optimizing the math for the circle routine. We just rotated a point about the origin to get all the different points on the circle. We're basically going to do the same thing. Here I'm going to look up the 2-dimensional rotation formula again. Okay, and we're going to copy this formula again so I can use it. Let's go ahead and just paste it in here as a comment. There we go. Okay, so that's that. I'm just going to space these out a little bit so I can see it better. And then this is actually times y1. It just got, I guess I didn't copy that part. Now we want to figure out the rotation of the x. So I'm going to make an rx for rotation x is now going to be the x, the initial x times the cosine, and the initial x is just what we got back here. That's going to be your sx. Okay, so sx times the cosine, and we'll get the cosine from the transform. That's cosine. Now we're going to subtract the sine times the original y, and so I'm going to put the original y times the sine. That's the whole transform on the x. Let's do the transform on the y. Let's see, that is x times the sine, and then we're going to add y times the cosine. So we're going to add sy times the cosine. So now we've scaled, we've rotated. Let's go ahead and work on translation. And translation is going to be relatively easy. All we have to do is add the amount we want to move. We'll just have a translation x for tx will be, so we're going to take the result of the last transform. We're going to put it down here, and we're going to add now the amount we want to translate, which will be the position x. And then we'll just do the same thing for the y. So the translated y is going to be the rotated y plus the position that we want to translate. There we have everything done. We've scaled, we've rotated, and we've now translated, and we can just return a new vector with the values. And so tx and ty ended up being our final values, and so we'll just send those back out like that. And once we finish writing this transformation class and optimizing it, it's going to be on par with the vector transformation function that comes with the Vector2 class. But the big win is going to come in memory usage and also in the actual creation of the transformation structure. We had to create a matrix here for the scale. Then we created a rotation matrix, and then we created a translation matrix, and we multiplied them all together. And the big win for us is going to come in the creation process. For us, creating the transform is basically doing 2 trig functions and 6 assignments in here. So really pretty quick operation. If we open up the matrix class that came with MonoGame, if we use that one, not only do we have 16 floating point values, and back in the game class, every time we do one of these multiplies, let's look up the multiplication function. Okay, so there's multiply. Okay, so here's the actual multiply function that they use. Every time we do one of these multiplies, it has to do all of this. And we can add that up, so it's 1, 2, 3, 4 multiplies and 3 adds for every component. And so if we multiply that by 16, that's going to be 4 multiplies times 16 components. So it's going to take 64 multiplies to do the entire operation. And then we have 3 adds times 16 components, and then 48 adds. So every time we multiply, we have to do 64 floating point multiplies and then 48 floating point adds. And not only that, but if you look at this, we're actually doing 2 multiplies. And so we have to do each of these numbers times 2. So we're going to have this times 2, and then we're going to have this times 2. We're actually ending up with 128 multiplies and 96 adds just to get this done right here. Whereas we can create this full transform just by doing 2 trig functions, 1 sine and 1 cosine. So now let's go ahead and use this transform function to do what we were doing before. In the shapes class, instead of passing in the matrix transform, let's pass in a flat transform. Instead of using the Vector2 transform, we're going to use the one out of the utility class. Pretty much exactly the same code. Now we're just using our transform that we created instead of the one provided by MonoGame. Back in the game class, we're going to comment this code out. Let's create our own transform. And we're going to create it exactly like we did the one before. So we're going to pass in for the position, we're going to do 0, 100. So that'll be a Vector2 at 0, 100. The rotation was the 2 pi divided by 10, so let's just copy and bring that over. That'll be the angle of rotation. And the scale we had at 1. This should look exactly like we did before. Okay, there we are. And if you look at it, we got it, it's in the same position, it's been rotated the same amount. We can go ahead and apply a scale. Let's say we want the scale to be 2, so now it should be twice the size. There we go. This here, the creation of the transform, is really optimal. It looks really good. I would like to now optimize in our utility class, this transform routine. I'm going to make a copy of this. This is going to be the original one. I'm going to call this transform slow, and I'm going to make a new one called transform, just transform. This will be the new optimized routine. I'm going to get rid of all these comments so we can just kind of look at the code directly. I'm going to start combining up terms to see if we can optimize this code at all by maybe pre-computing some values. And so I'm going to get rid of this whole scale here. Instead of saving the scales individually like this, I'm actually going to compute these scales down here. So everywhere it says SX, I'm going to put in this position X times transform scale X. So let's copy that. In fact, let's just cut it. And everywhere I see SX, I'm going to paste this in. Okay, so that SX and then this SX. And then same thing with the Y. Take the scale on the position. Let's cut that out. And everywhere I see SY, I'm going to paste that in. And then we'll paste it in there. So we just got rid of that. That's gone. And that doesn't really give us much of a win. It's just, in fact, it may be a loss at this point because now we're actually doing this multiplication twice, whereas before we were doing the multiplication once. So I'm doing this scale here on the X, and then here on the X, then I'm doing the Y here, and then the Y here as well. But if you look at this, we can actually start pre-computing some of these terms and saving those, which should save us some multiplications. Looking at this, and I've got this scale X times cosine, and I want to take these values and I want to save them as pre-computed. I want to take these values and I just want to pre-compute this part. So I'm going to have 4 values I'm going to pre-compute. I'm going to save this one, and it's going to be the scale times the trig function. So here's this scale times the trig, and there's going to be 4 of them. Here's this one, and this one. Back in our transform class, let's go ahead and change this a little bit. Instead of saving the trig functions and the scale values separately, I'm going to combine them. So let me go ahead and look at what we have here. So the first one is going to be the cosine times the scale x. All right, so let's go ahead and save that. I'm going to call this cosine scale x. And we're going to have 4 of these. The next one is, I'll just take this one over here. Actually, let's do the sine and cosine x. So the next one is going to be the sine scale x. And the other 2 are going to be the sine scale y and the cosine scale y. And so I'll just copy this and paste it, and we'll just change this to the y's. Okay, we're going to get rid of these sine cosine scale values. So now that we have just the combined values. And you can see it doesn't change the size of our transform at all. The size stays the same, right? We have 6 values that we need to store. Over here, we're going to pre-compute the sine and cosine. Will be the sine of the angle, and then we'll just pre-compute the cosine as well. And let's get rid of all of this. We're going to start just filling in these values. So the first one is the cosine times the scale. That'll be our cosine times the scale x we passed in, because this is the cosine scale x. I'm going to copy this and just put these in here 4 times. So then we're going to have the sine x, this one's going to be the sine, and this one's going to be the y. Okay, so we have the cosine scale x, the sine scale x, the cosine scale y, and the sine scale y. Okay, so this one, we just need to change these values now. So this will be the sine, this will be the sine, and then these 2 will both be y. Now, we actually do a little bit more in the creation of the transform. We do 4 multiplies, whereas before we were just doing the trig functions. Now we do the trig functions and we do 4 multiplies. But when you actually go to do the transform later on, it's going to save us quite a bit of computation. I'm just going to copy this and paste it down here in our overloaded function so we have the same thing. And instead of components, we're just going to multiply it by the scale. Back in our utility class, instead of multiplying by the scale x and then multiplying by the cosine, we want the transform cosine scale x. And same thing over here. Instead of using scale y times the sine, we're going to do the transform times the sine scale y, and we get rid of that. Down here, this is going to be the transform, and we want the sine scale x. The sine scale x, and so we'll get rid of that code. And then finally we want the transform, and this is going to be the cosine scale y. And we'll get rid of that. Okay, so that's going to do exactly the same thing we had before, except for now we have these values pre-computed, and the size of the transform is actually exactly the same as it was before, so it's pretty much a win-win for us. In order to allow the compiler to know exactly what's happening and to make as many optimizations as it possibly can, I'm just going to combine all of these values. Instead of doing this and then doing this, let's just put it all in one. Let's add in this immediately right here. Same thing for the y. We'll just add in the position. So it's going to do the scaling and rotation here, and then it'll add in the translation at the end. All right, and so we can get rid of that. We can make this actually even simpler by getting rid of these two lines completely and just putting these values directly into our new vector. Let's get rid of the tx and ty that we had here before, and let's just pass in these values directly. And I'm going to put these on separate lines since they're kind of long. And then let's just drag that down here. And we get rid of that line completely. And this is our final optimized code. Okay, and you can see we have how many multiplies? So 1, 2, 3, 4 multiplies, 1, 2, 3, 4 additions and subtractions. It's now giving me errors on the old one because transform doesn't have a scale x and does not have a sine cosine by themselves anymore. And so let's comment out our old transform code since that doesn't work anymore. Let's go back here. This should be exactly the same when I go ahead and run this. And there we are. Looks exactly the same. We've rotated slightly. We've scaled. First we scaled, we rotated slightly to the left, and then moved it up 100 points. And we can make this even just a little bit cooler by, instead of having a constant rotation, let's go ahead and specify an angle of rotation. So let's have an angle. I'm going to say that starts at 0. I'm going to now, inside the update function, let's increment the angle. So I'm going to say the angle is going to be incremented by pi over 2. Okay, so that's 90 degrees. It's going to do that much. It's going to go pi over 2 every second. And the way we force that to be every second is we bring in the game time and the elapsed game time and the total seconds. What this is going to do is it's going to say I want the angle to advance by pi over 2 radians every second. Now we can just take this angle and I can put it into our transformation. When we create our transformation, I'll just put that in here instead of the constant 2 pi over 10. So this will be the angle, and we should see some rotation. And so that's how we're going to transform points in our game library. Now there's one final thing that you may want to do with our transformation structure. We may want to convert our transform structure into a transformation matrix provided by MonoGame. You may need a matrix to work with shaders, different types of shaders, and things like that, or or you may want to just work with MonoGame and occasionally provide a MonoGame matrix. And so we're going to want to just provide a function that will convert our transform structure into a 4x4 MonoGame matrix. Inside our transform, this will return a matrix, and I'm just going to call this 2 matrix. We'll have a result, and initially it's just going to be the identity, and we'll return that result. And there's only just a few fields we need to specify. The first field we need to specify is the M11, and that's going to be the cosine times the scale x. And I'm just going to copy this because we're going to do this 4 times. Okay, then we'll do the M12, and that is going to be the sine times the scale y. Next we have the 2,1 and the 2,2. 2,1 is going to be the sine scale x, but it's going to be a negative sine scale x. And then 2,2 is going to be the cosine scale y. But that will create the matrix with the rotation and scale that we currently have. Now we need to also provide the translation, so that'll be M41 is going to be the position x, and the M42 is going to be position y. And so just filling out a matrix with these values that we've already calculated will then provide a matrix that does exactly what we're doing with our own flat transform structure. So real easily we can provide MonoGame with a matrix if we need to.